Hey guys, I'm Jay. Today is my LeetCode review vlog on 112th problem, path sum. We are given the root of a binary tree and an integer target sum. We have to return true if the tree has a root to live path such that adding up all the values along the path equals target sum. Let's see example 1 here to understand this problem easily. We got a binary tree here and the root to live path with the target sum is shown here, which is 5 plus 4 plus 11 plus 2, which equals 22, which is the target sum. So we'll return true. And for example 2 here, we got two paths. The first path is 1 plus 2 equals 3 and 1 plus 3 equals 4. And there is no root to live path with sum 5, so we'll return false. And for the third example here, we got an empty binary tree here and the target sum is 0. As the tree is empty, so there are no root to live paths, we'll return false. Then let's get started with our innovation to solve the problem. The main idea to perform a tree traversal, like the depth first search and the binary first search. We'll explore all the possible root to live paths. And for each path, we'll check the cumulative sum of node values as we traverse down the tree. Once we reach a leaf node, then we'll check if the cumulative sum matches the target sum. And there are 3 methods to approach this problem. First is called recursive depth first search using recursion. First, recursive depth first search. And the second is called iterative depth first search using a stack. And the third approach is called breadth first search using few. Then let's get started by the first approach, recursive depth first search using recursion feature. And the first line of code is we have to check for the bad case. If the root is null, we'll return false as the problem asks for. If root equals null, then we'll return false. Next, we have to check if we reach a leaf node. If so, we'll check if the remaining target sum equals the node's value. If root.left equals null and root.right equals null. If so, we have to check if root.value equals target sum. If so, we'll return true as we found the proper path. But if the condition is false, then we'll continue the recursion as we didn't reach a leaf node. And for the further code, first we have to update the remaining target sum. Remaining sum equals target sum subtract root.value to prepare for the next recursion. And then we'll use the logical OR, a double pipe, to check if either the left subtree or the right subtree contains a valid path. The code is return and recursively call path sum with root.left and corresponding remaining sum, or has path sum of root.right and remaining sum. And that's all the code for the first approach. Let me submit. Let's submit the code and check for the correctness. And yes, our code got accepted. And then let's analyze the time and space complexity. So the time complexity, it is big O of n, as n stands for the number of nodes in the binary tree. As we visit each node for only one time during the traversal. And the space complexity is also big O of n. This is because the recursion stack will have a depth of big O of h, and h stands for the height of the binary tree. And there are two cases. For balanced binary tree, h equals big O of log n. But for a skewed tree, the h could be big O of n. So let's take the worst case. And then let's discuss the second approach, which is the iterative depth-first search using a stack. Then let's get started with code and detailed explanation. First, we have to check the bad case 2. If root equals now, we'll return false. Then we'll create a new empty stack to store pairs of current node and corresponding remaining sum. So the type is stack of pair of tree nodes and integer. Let's call it stack with a new stack to it. Then we have to push the root node and corresponding updated remaining target sum into the stack. Stack.push root node and target sum subject root.value. Then we'll create a while loop to traverse all the nodes. While now symbol stack is not empty. And for each iteration, first we have to pop up a node from the stack and check if it's a leaf node. Pair of tree node and integer. Let's call it pair equals stack.pop. Then we have to get the current node and corresponding remaining target sum. Tree node here equals pair get key and remaining sum. Remaining sum equals pair get value. Then we have to check if the node is a leaf node. If so, we'll check if the remaining sum equals 0 further. If node.left equals now and node.right equals now and remaining sum equals 0. If so, which means we found a proper path and we'll return true. Remaining sum equals 0. If so, we'll return true. But if the condition is false, then we'll continue the while loop. We will push the right subtree and left subtree, if they exist, to the stack with the updated remaining target sums. and we can push the right subtree first. So the left subtree would process first in the stack. If note the right is not equal to null, then we'll call stack.push with a new pair. The first one is node.write and updated remaining sum, and the code is remaining sum subtract node.write.value, and it's very similar to the left subtree. If node.left is not equal to null, then we'll push it into the stack. New pair of node.left and remaining sum subtract node.left.value. And out of the while loop, which means we traverse all the paths and we didn't find the correct path, so we'll return false. Then let me submit the code and check for the correctness. Oops. Method push in class stack cannot be applied to given types. Let me check on this. Oh, it's my fault. I forgot to create a new pair to it. Let's submit the code again and check it again. Yes, our second approach code got accepted. And then let's analyze time and space complexity. The time and space complexity is both big O of n, and n stands for the number of nodes, as we visit each node for one time, and for the worst case, as good tree, we could store all the nodes into the stack. And then let's come into the final approach, breadth first search using a queue. So for the third solution, we'll create a queue to traverse the binary tree level by level. And we also will maintain the current node and the remaining sum at each state, and we'll check if the remaining sum is equal to 0. If so, we'll return true. Then let's start with the code. The very first state, we have to check for the bad case. If node equals null, we'll return false. Then we'll create a new empty queue of pair of tree node integer. Let's call it queue equals a new linked list. And then we'll start it at the root node of the tree and enqueue the root node and the corresponding remaining target sum. The code is queue.add a new pair with root node and target sum. Subtract root.value. Next, we'll create a while loop to traverse all the tree nodes. While not symbol. Queue.is empty. And for each iteration, first we'll dequeue the from node, pair of tree node, and integer. Let's call it pair equals queue.poll. And then we have to get the current node and corresponding remaining sum. Tree node. Let's call it node equals pair dot get key and integer remaining sum equals here get value. Next, we have to check if the node is a left node. Node.left equals now, and node.right equals now, and logical and remaining sum equals 0. If so, we just return true as we found the proper path. But if the condition is false, we'll continue the traversal by enqueuing the not now left subtree and not now right subtree with updated remaining sums. Let's enqueue the left subtree first to obey the sequence of the pre-order traversal. If node.left is not equal to now, then queue.add a new pair. New pair of node.left and remaining sum. Subtract node.left.value. And it's very similar for the rest subtree. So let me just copy the code and change the name. If root.right is not equal to now, then we'll add the right subtree. Oops, rest subtree, and remaining sum subtract node.right.value. And out of the while loop, which means we traversed all the paths, but we didn't find the proper path, so we'll return false. Let's submit code and check for the correctness and analyze the time and space complexity. Yes, our code got accepted. So the time complexity is big O of n as we traverse each node for only one time. And the space complexity, it is also big O of n comparing with the first and second approach, as we use an extra queue, and in the worst case, for example, a skewed tree, we could store all the nodes into the queue. So the overall space complexity, it is also big O of n. And that's all of the code for this problem. And I highly recommend you guys to visit my online GitHub page here. You can see all the problem description, intuition, Java code with different solutions, and very detailed code explanation, and the final time and space complexity analysis. And you can also visit my online GitHub repository here, which contains all the nodes and codes to build this online GitHub page. And I'll put those two links on my YouTube description below. And thank you guys for watching. I'll see you next time. Bye bye.